So PPT is visible.
Yes.
So good afternoon, dear student. So we are going to discuss, yes, good afternoon. We are going to discuss mm, the underlying theory and the process of experimentation and some results of the experiment 6. The title of the experiment is Studies on Spectral Composition, and CCT. CCT stands for Correlated Color Temperature of Different Lamps. So this is the title of the experiment, and myself is Vishwanath Roy and Sangita madam. Both we are actually going to present this. So these are the following objectives: to observe the physical structure of different types of lamps, CFL stands for compact fluorescent lamp, HID stands for high intensity discharge lamp, and their circuits, to study the spectral composition of different lamps with constant deviation spectrometer, to measure correlated color temperature, CCT, henceforth we call it CCT, correlated color temperature. We will discuss all the terms of different lamp with chromometer, to correlate the measured CCT and spectral composition of different lamp. So these are the 4 objectives of the experiment. Out of the 4 objectives, you see that there are 2 instruments we are going to discuss about: constant deviation spectrometer, one instrument, with which we can get the values of wavelength. We can measure the wavelength with this instrument. And another instrument is chromometer, with which we can measure the correlated color temperature, CCT, of different lamp. And the last portion is the theoretical discussion that the measured values of the wavelength can be theoretically correlated with the measured value of CCT. That is the last portion. Actually, there are 3 sections of this presentation. The first one will come, the background theory will come first, and then working of the instrument used. There are 2 instruments that I said just now, and then experimentation and results with discussion. I am going to discuss on these 2, the first 2, background theory and working of the instrument, and Sangita madam will discuss about the third portion, right? So anywhere you have any doubt, you just stop me, unmute yourself, stop me and raise the question. So these are the lamps will be used. The first one comes the incandescent lamp. This is the most commonly used lamp in earlier days. Now the LED already evolved in the market. So this is the lamp, the physical appearance of the lamp when there is no power, and this is the physical appearance of the lamp when its power is fed to the lamp. This is tungsten filament lamp. By the physical process of generation of light, the lamp is also known as incandescent lamp. And this lamp is low pressure sodium vapor lamp. In short, it is LPSV, is for sodium, or it is called SOX, SOX lamp. The power is fed to the lamp, the appearance of the lamp is like this. So the golden yellow color is emitted by the lamp. The radiation of the color as perceived by us is the golden yellow. And this is the physical structure of the lamp. See, this is the discharge tube actually. Long discharge tube, here is the folding, right? This is a discharge tube. This lamp is known as discharge lamp. The similar low pressure sodium vapor. Similarly, these 2 types, you know it is called compact fluorescent lamp. These 2 are also low pressure mercury vapor lamp. And this is the spiral discharge tube. In the same way, this is the color appearance of the lamp. The color is all the bluish white. That's why it is called cool white. There is no connection of temperature. The cool means when we look at the eyes under daylight, the color of the eyes appears as bluish. That's why this is cool daylight type, cool white CFL lamp, and whereas the color of the warm white CFL is yellowish. But this yellow and this yellow are totally different. So this is the physical appearance of the lamp when there is no power fed to the lamp, and this is the physical appearance of the radiation coming out. The color of the radiation is that are actually we are going to investigate with the help of this experimentation. So if we want to know the constituent wavelength of the uh, radiation emitted by any lamp, then we need one instrument that is spectrometer. You know that the spectrometer actually, the function of the spectrometer, the basic function of the spectrometer is to the split the wavelength which comprises the incident radiation, right? So this is simple pictorial representation of these phenomena. These phenomena, optical known of the optical, sorry, sorry. The name of the optical process is called the dispersion, right? The name, the refraction is taking place here. So when white light incident on one surface of the prism, the other from the other surface after emission, they are actually split into constituent wavelength. I'm going to mute my, I have to mute my. So this phenomena is the dispersion. So by dispersion, we are getting, we can get the spectrum of the incident radiation. So whatever may be the incident radiation, by the dispersion, we can get the spectrum. This is actually the optical, sorry, the optical process, as I told you, the dispersion. And this is the spectrum of the entire electromagnetic optical radiation. We are not confined here only on the visible part of the electromagnetic radiation. Rather, the ultraviolet radiation, visible radiation, and infrared radiation, the entire span actually constitute the optical radiation, what you call the optical radiation. And when you fed the power of to any lamp, we are getting the electromagnetic radiation, the limits within this range, ultraviolet, visible, and infrared actually. So the light source actually, primarily emits the visible radiation most, but it depends on the type of the light source. Say, for example, if we consider the incandescent lamp, then we will see it actually radiates maximum radiation goes to the infrared radiation. A very small portion, relatively small portion goes in the visible radiation. Maximum goes in the infrared radiation. That's why we feel heat in presence of the incandescent bulb. So why the name is the visible radiation? Because from 400 nanometer to 800 nanometer, this is the range of the visible radiation. It has the capability to stimulate our visual system, that is eye. We can see when this amount of this range of electromagnetic radiation is allowed to incident our eye, and we can see the image out of this radiation. So by spectral composition, we mean that I just said, what are the constituent wavelength? So depending on the presentation, there are two types. We can classify the two types. One is one-dimensional chromatic presentation and two-dimensional presentation. We will come later on two-dimensional presentation. Let us discuss what is one-dimensional chromatic presentation. This chromatic means actually the visual presentation. This is the picture, one-dimensional chromatic presentation. And visible with the help of constant deviation spectrometer. That's why we are going to discuss the what actually is seen. This is the exactly is seen when a constant deviation spectrometer is allowed to get light from a discharge lamp, right? So this is one-dimensional chromatic presentation. We can see the different wavelength, and see the beauty of our visual system is that we can perceive different wavelength as different color. That is the beauty of our visual system. We can perceive, again I repeat, we can perceive the different wavelength as different color. Say for example, here, the optical radiation emitted in this wavelength, we can see it as yellow, whereas optical radiation, where wavelength is around 400 nanometer, we can see it is as violet. So same is applicable for all other color. So from 400 nanometer to 800 nanometer almost, the different wavelength, we can differentiate different wavelength by virtue of perceived color. So color is not associated with the radiation, right? I repeat, color is not associated with the radiation. It is the property of our visual system that we can see, we can differentiate different wavelength as different color. So this is one-dimensional chromatic presentation. And these one-dimensional chromatic presentations are of two types. One is continuous wavelength, and other is line spectra. This is called the continuous spectra. This is called the continuous spectra, because it is not possible for us to discriminate different wavelength. It is the gradual variation of color from lower wavelength, which is red, portion of wavelength is violet, and higher portion of wavelength is red. So here it is from higher wavelength to lower wavelength. Here it is called line spectra. Why? We can see the line because the in between the two color there is no emission here. Since there is no emission of optical radiation in between wavelength, it appears to us as dark region. So two colors are separated by dark region. So what is the physical meaning of this dark region? The physical meaning of this dark region is that there is no optical radiation emitted in this wavelength, right? This is the physical meaning of this dark. And the line spectra is visible because of the presence of the dark region. So here, selective radiation is coming out from the lamp. Here, there is no selectivity. Continuous radiation from 400 nanometer to 800 nanometer is emitted by the lamp. On the other hand, the two-dimensional presentation is known as spectral power distribution. Why? Because in this presentation, the associated power of radiation is also plotted along with the wavelength. The axis actually plots the wavelength in nanometer, and the ordinate plots the relative spectral power. It is relative spectral power. That's why there is no unit here. So maximum is 100. So associated power is also plotted. That's why it is spectral power. So power terms appears here, because this plot gives me not only the value of wavelength, but also what is the associated power. So two-dimensional plots are represented by radiant power at a wavelength and its color. Optical power is maximum in the emitted radiation. So it is the wavelength here. It is the wavelength here where the optical power emission is maximum, whereas this is the wavelength here where optical power emission is minimum. So we can have some idea where the amount of optical radiation emitted at different wavelengths. So information of emitted power is available from the two-dimensional plot, what we call the spectral power distribution. In short, we call the SPD. SPD, spectral power distribution, right? And there are a lot of information we can get out of the spectral power distribution. What is the nature of emitted energy and over a range of wavelength? Thermal radiator gives continuous SPD, whereas gas discharge lamp shows line spectrum or the discontinuous spectrum. And it provides information about how much portion lies in the visible and out of the total amount of radiation. So this is possible when we have the information of the entire optical radiation. But this figure, the instrument used to have these data is only operates in the range of 400 nanometer to 800 nanometer. That's why we have no information regarding the UV or IR. But from this diagram, we can have the idea there are some radiation in these lower portion of these 400, that is in the UV, and there is also some radiation emitted in the IR, right? But what is the power? It is not possible for us to know from this diagram. So that's why we get some impression about the what is known as in our work. Actually, we concentrate over there. The constant deviation spectrometer gives us the information only regarding the wavelength. So one-dimensional means the information is available about the color and wavelength. We can have the visual impression of the color, and we can measure what is the wavelength of the color. That much we can uh, measure with the help of constant deviation spectrometer used in this experimentation. These are the pictorial representation of the spectral power distribution, right? This is the spectral power distribution of tungsten incandescent lamp. And if you follow, all are in the relative scale. If you follow the pattern, you see higher the wavelength, higher is the power, associated power, optical power. So you can gauge that beyond 800 nanometer, that is in the IR region, the optical radiations are there. And it is true. So that's why the radiation coming out from the tungsten filament lamp is hot, actually, because the significant amount of IR radiation contains the radiation. And see, it is a continuous spectra, right? This is the example of continuous spectra. And here, this is the example of daylight, that is the natural light. It is called daylight 65. It is natural light, the daylight radiation. It is almost white because all wavelengths are present in this portion, 400 nanometer to 800 nanometer in equal proportion. That's why it is white. Whereas if you look at here, the amount of radiation in the yellow region and red region is higher. So the color appearance of this tungsten filament lamp is, this is the spectrum of the low pressure sodium vapor lamp, the SOX. The lamp we will discuss in the experimentation portion. And see, it is almost single wavelength, but it is not single wavelength, almost single wavelength. Why we can take this almost single wavelength? Because the optical power emitted at the other wavelength are insignificant. The major emission of the optical radiation in the 589, approximately 589 nanometer, and it is the golden yellow color. On the other hand, in case of high pressure sodium vapor, this is the spectrum. In case of metal halide lamp, these are called the HID lamp, metal halide lamp. This is the nature of the spectrum. Now, the spectral power distribution of the warm white LED stands for light emitting diode. Now, in the smartphone or every other normal traditional phone also, if there is a torch light is made of LED, light emitting diode. And the cool white light emitting diode and the warm white light emitting diode the term warm white comes because of the fact that the emission, actually, the significant amount of emission lies in the yellow red region. So the color is actually yellow. And we know that the color of fire is yellow. That's why it is named as warm white, right? Well, here the blue portion is more, so color appearance is bluish white. And the LED, this is both LED, basically it is the blue chip. The blue emission is coming out from the LED chip, and there is a phosphor. Phosphor is covered over the blue chip, and the phosphor actually converts this some portion of the blue in the yellow, green, red region, and we are getting this portion of emission from the phosphor, right? And this portion is from the blue. And it is the amount of phosphor and the type of the phosphor that from the same blue chip we can get both warm white LED and the cool white LED. So this diagram, in short, this diagram actually the pictorial representation of the spectral power distribution of different light sources. And this spectral power distribution gives us some idea what is the color appearance of the lamp. And that color appearance of the lamp is measured with the instrument, that chromometer, and that actually numerically represented by this term correlated color temperature. So CCT, which stands for correlated color temperature, this actually the numerical representation of the color of white lamp, right? Again, I repeat, what is CCT? CCT is, what is CCT that I'm going to discuss? But CCT actually represents the color appearance of the white light source. And white light source ranges from the warm white to cool white, right? This is the subjective description of the color, cool white, that is bluish white. The subjective description of color, yellow, color of yellow white, that is warm white, right? Now, what is CCT? CCT is the absolute temperature of the black body radiator. Absolute means it is expressed in Kelvin. That's why it is absolute. So CCT actually, the temperature of the black body, whose color appearance mostly nearly it is a candle. What is the CCT? 1900 Kelvin. So when a black body is heated at 1900 Kelvin, then color appearance of the black body is very close to the color appearance of the candle. And we know that the black body, there is a law, Wien's displacement law, W-I-E-N, Wien's displacement law. From the Wien's displacement law, we know that as we go on increasing the temperature, lambda m into T equal to constant, as we go on increasing the temperature, then it color shifts from yellow, from red to yellow, then yellow white, then blue white. So this phenomena actually utilized to represent color in terms of the temperature of the black body radiator. And this CCT actually we measure with the help of chromometer. Now, there is a gradation of CCT, range of different ranges of CCT. When CCT is less than 3200 Kelvin, we call the warm. When it is more than 4000 Kelvin, it is cool. And the same room illuminated by lamps of different CCT look like this. Now, we are going to discuss about the instrument we use for the measurement of this. But before that, if you have any question on the background theory, you can ask. Have you any question on this portion?
So relative power is with respect to
relative power is respect to the maximum. Relative power is with respect to the maximum power. Yes. Say suppose here maximum is numerical value of maximum is 10. Suppose for example, all values are divided by Okay.
Sir, there is some interruption in your voice in between.
Oh, that
The
is
voice
throughout.
is breaking.
Oh my God. That is throughout my
Yes, sir.
presentation.
Yes, sir. Yes, sir.
Oh my God. So which portion you missed? I don't know.
Sir, can you repeat the CCT portion?
Yes. CCT portion I am going to repeat, but actually the color appearance, CCT actually measures the color measures the color appearance of the radiation. CCT measures the color appearance of the radiation, whether of white light. The white is the yellow white or neutral white or blue white. See, when you look at here, we see that the blue emission is more with respect to the yellow red emission. That's why the color of this lamp appears as bluish white. On the other hand, the red yellow portion, the emission, optical emission in the red yellow portion is more as compared to the blue. That's why color of this lamp appears as yellowish, and we call the warm white. CCT actually physically represents the color appearance of white light source. And by white light source, there are three ranges. We call the ranges are the warm white, neutral white, or cool white.
Okay, sir.
The warm white means yellow white when the color is, the value of the CCT is lower. So when the CCT value is lower, of the order of around 3000 Kelvin, the CCT value is more than 4000 Kelvin, then we can expect that the color appearance of the emission is bluish or cool white. And why? This we can explain with the help of this diagram. What is the physical reason behind that? This can be explained with the help of this. What are the wavelength and the associated power? But in our experimentation part, we actually we can measure the wavelength of different color with the help of constant deviation spectrometer. We cannot measure the associated power. Okay. Now the instrument, we are going to use the two instrument. One is constant deviation spectrometer. This is the physical appearance of the constant deviation spectrometer. The wavelength range is 360 nanometer to 800 nanometer. That is in the visible range, because it is obvious, because whatever we can measure here with the help of our eye, so beyond this range, it is not possible to measure anything. And this is chromometer. The range is 2000 Kelvin to 10,000 Kelvin. What is constant deviation spectrometer? Constant deviation spectrometer, actually the prism that is used is Pelian-Broca prism. There is a special type of prism I am going to discuss here. So what is the step of the measurement? The first step is to calibrate the constant deviation spectrometer, CDS, using a calibrated calibration source. Usually you take the low pressure sodium vapor lamp. What is low pressure sodium vapor lamp? I actually, this is the spectrum of the low pressure sodium vapor lamp, and this wavelength is known, 589 nanometer, 589.6 nanometer. So since the wavelength of radiation is known, the first step is the calibration, and second step, with the calibrated constant deviation spectrometer, we can find out the error. That Sangita madam will discuss. And then we can proceed to measure the wavelength of the different color emitted by different test lamp. There are three portions of the constant deviation spectrometer. The first one is the collimator here, collimator. Lamp is to be placed here. Source means lamp. Lamp is to be placed here. So the collimator is to allow the received radiation from the lamp, and the purpose of the collimator is to convert the diverging light rays into parallel beam of light. Then here the lamp, so here the diverging rays are collected by the collimator, and the optics is here, and the task of the optics is to convert the parallel beam into, convert the diverging beam into parallel beam. And this parallel beam is allowed to incident here. Within the box, there is a prism that I am going to show you. The task of the prism is to split the incident parallel beam into constituent wavelength, creating the spectrum of incident light. And then it is the constant deviation, because deviation is 90 degrees always. So this is the direction of the incoming beam, this is the direction of the incoming beam, and this is the direction of the refracted beam. So you know what is how deviation we can calculate. This is the deviation we can calculate, or this is the deviation we can calculate. The deviation is always constant, 90 degree. So with the help of the calibrated drum, there is a drum here. There is this drum here. So with the help of the drum, the prism, we can rotate the prism, and accordingly, a color is selected at the mid of the telescope field of view. And when any color is at the mid of the telescope axis, then from the instrument, deviation spectrometer, collimator.
Sir, your voice again got interrupted.
আরেকবার রিপিট করবেন একটুখানি
ড্রামের পরটা একটু রিপিট।
Oh, so with the help of the drum, we can rotate the prism. So while we rotate the prism, you know from the theory that I'm coming here. 1 minute. You know, this is the axis, z-axis. With respect to the z-axis, if we rotate the prism, that angle of incident actually changes. When angle of incident changes, then we can select the different color, right? Because the spectrum looks like this. This is the this is the physical appearance of the spectrum, right? And we have to bring down different color at the axis of the telescope by rotating the drum. So what is the purpose of the drum? To rotate, the purpose of the drum is there is a mechanical arrangement. When you rotate the drum, then actually it rotates the prism with the respect to the z-axis. So when prism gets rotated, then angle of incidence actually changes. So when angle of incidence is changing, then we can select the different color, and we can bring down different color at the axis of the telescope. The axis of the telescope here. This is known as the eyepiece, when we can put our eye here to see the spectrum here. So this is the axis of the telescope, this is the axis of the collimator, right? Right. And you see the deviation is constant, always 90 degrees. That's why it is constant deviation spectrometer. So the prism is very special. It is Pellin-Broca prism that ensures that final deviation of the light rays that passes through the prism is always 90 degrees. And rotating the prism allows different wavelength to be viewed through, that is the drum, with an attached calibrated drum. The user of the device may rotate the turnable unit until they can observe the light through the telescope. At this point, they can read the wavelength of the light from the drum. So there is a surface, in the surface of the drum, there is a scale of wavelength in nanometer, right? And there is a lens here. We can read the value from here, this opening, this small opening. And this is the physical appearance of the prism. And the optical diagram is shown here. The direction of the incident beam. It get total internal reflection here, and it comes here. You can go through this later on. I think you can understand the propagation of light through the prism. The main thing is that the angle between these two is 90 degrees. Any question on this constant deviation spectrometer? Okay. Next instrument is chromometer. The model is CL200A. it is the maker of the instrument is, you see, the Konica Minolta. This instrument actually we are using in our lab for the experimentation purpose, Konica Minolta CL200A. So the CL200A has the sensor. This is sensor actually. This is sensor. There are three sensors under this white diffuser. This is white portion is the diffuser. Sensors are not visible from outside. And this display actually, we can see we can get the values from display the T to color. We are not going to. We are now interested to value to read the value from here. What is the CCT? 5949 Kelvin. Now, what is written here? Let me read. The CL200A has sensors that closely match with the CIE. CIE stands for International Commission on Illumination, the apex body, international body on lighting, the color matching functions, which are intended to correspond to the response of the human eye to enable the precise color measurement. The measurement results can be displayed in the various the color notations such as correlated color temperature, or these are the parameter of different parameters of the color. We will concentrate here only on the value of T or correlated color temperature Kelvin. Now, what is meant by this CIE color matching function? Actually, we have three different types of cone photoreceptors. And this sensor, actually, there are three sensors, red sensitive, green sensitive, and blue sensitive. The three sensors are same response of the cone photoreceptors of our eye. And here, it is shown only the response of one photocell, one cone receptors. The spectral response of an ideal luminance meter would match actually it is V lambda, the spectral luminance efficacy function of photopic vision. So the solid line actually, the plot of the response of the sensor in CL200A chromometer, and the dotted line actually the V lambda. This is V lambda. Here it is not I, it is V lambda. So V lambda is the response of our cone vision, is known as photopic vision. And this diagram with that of our eye under photopic vision. So matching is very close. This matching is represented by the number, this F1. This matching is actually represented by number F1. The matching, the mismatch is within 6% mismatch, right? So this is specification of the instrument. This F1 prime represent the numerical value of the matching. It is within the 6%, right? On the other hand, this sensor is need to collect light from all other direction. So some cosine correction is necessary for this type of instrument. The cosine correction actually is done with the help of this white diffuser. And how cosine correction actually obtained, that is represented by this diagram. So what is written here, let me read. Because of the brightness at the measurement plane is proportional to the cosine of the angle of incidence, the response of the receptor must also be proportional to this cosine. So it is almost matching, right? The dotted line is the ideal one, and this continuous line is for chromometer is almost matching, and the mismatch is within is given by this value F2. This F2 value represents the mismatch. The mismatch actually within 3%. So this is the specification of the chromometer CL200A. What is the type of the photocell? It is the silicon type of photocell. It can measure the color temperature, correlated color temperature, along with other parameters that we are not going to discuss here, because the task here is to measure the TCP actually. So the next third portion that will be discussed by Sangita madam. And before leaving, let me inform me whether any question. Yes.
Sir, please repeat TCP because your voice gets
TCP. This is the symbol of the correlated color temperature. TCP is the symbol of correlated color temperature. Because this is taken from the specification of the instrument. What are the so much of parameter we can measure with the help of the instrument, but right now we can concentrate ourselves for the measurement of correlated color temperature, TCP.
Thank you, sir.
Okay, Sangita.
হ্যাঁ
সঙ্গীতা তুমি তাহলে এখন শুরু করো, নেক্সট কোশ্চেনটা বলো, at the end we will come back, right?
Okay.
Thank you. So if you have any question, you may also write down in the chat box. There is a chat box here. You can place your question here. We will discuss at the end of our discussion. Okay.
Is it visible? দেখা যাচ্ছে?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Visible.
So, sir, I've already discussed about the two instruments, the constant deviation spectrometer and the chromometer. Now, using these two instruments, we will measure the spectral composition and the CCT of these four lamps. So, sir has already shown this picture. The first one is the tungsten filament lamp or the incandescent lamp. Here you can see that it will emit some yellowish kind of light. You have already seen this lamp here in your house, maybe. And the second one is the low pressure sodium vapor lamp or the LPSP lamp. Here the color appearance is golden yellow type. And then the two type of CFL. The first one is cool white CFL, means it will emit bluish white. And the fourth one is warm white CFL, which will emit yellowish white. Now, this yellowish white or bluish white, these are very subjective. So to quantify them, we will use the constant deviation spectrometer to measure the corresponding wavelength for all the colors present in the light coming from those sources, and the chromometer for measuring the CCT. So you can see the first figure, which is an incandescent lamp. Here you can see it's written as 60 or 230 volt, the wattage and the rated voltage. Here you can see it's a 35 watt low pressure sodium vapor lamp. And this the third one is cool white or warm white CFL. So you can see in this third figure, it is written as 11 watt, 220 to 240 volt, rated voltage, current, etc. Now say we already know that the incandescent lamp will emit some yellow kind of light, and from the LPSP we will get the pure golden yellow color. But if you go to the market and if you see one CFL, so without providing power, you cannot say whether it is bluish white type of light or yellowish type of light. So in that case, you have to see the specification of the lamp. So if something like this cool daylight or 2700K or 6500K is written over the lamp, so without providing the power, you can say the color appearance of the source. See, in this CFL, we cannot say whether it's cool white or warm white. But from the specification, this cool daylight, we know that it will be something more than 4000 Kelvin, or it will emit bluish white. And if something like this 2700 or 3000 Kelvin is written over the lamp, it will emit the yellowish light or the warm white light. Now, coming to the procedure of this experiment, we have to observe the physical construction and the components of the lamps and study the lamp circuit. Second, we have to place the lamp properly with the constant deviation spectrometer. So in this black box, we have the low pressure sodium vapor lamp. And there is a small opening, this one. So we have to connect the lamp with the power supply. Then we have this collimator. Here we have the prism, and here we have the telescope. So here the observer will look through this telescope. You have to sit here and you have to put your eye over here to the telescope, so you can see the spectrum in this prism, in this part. And by rotating this drum, we can rotate the prism and we can see the color. We can observe the colors one by one in this part, and we can measure the corresponding wavelength over here. Now there are very two narrow openings over this collimator and the telescope. Like when we click any image, we focus on this particular object. Similarly, here by adjusting this two slits and the drum, we have to focus the spectrum so that we can observe the color clearly over here, and we can measure the corresponding wavelength in this drum. So you have to adjust the collimator and the telescope to bring the image of the spectrum at focus of the eyepiece of the telescope. This is the telescope. So you have to rotate the drum, means you have to rotate the prism, and it will be at the focus of the eyepiece of the telescope. Now, this is the instrument, constant emission spectrometer. Here we have the source, the low pressure sodium vapor source, and this is the appearance of that lamp when it is in on. Now, why we were starting this experiment with low pressure sodium vapor lamp? To check the error of the instrument or to calibrate the instrument. Like whenever you use any voltmeter or ammeter, we check the zero error, right? Similarly, here also we have to check whether there is any error in this instrument itself or not. So we will start the experiment with the low pressure sodium vapor lamp because it emits a monochromatic color, or the main radiation is in the yellow region, which is at 589.6 nanometer. So that value is already known to us. So we'll start the experiment with LPSP. We'll place the lamp here. We have to sit here and look through this telescope. So in this prism, we can see this entire spectrum, but not at a time, because this is a very narrow opening. So to see all the colors one by one, we have to rotate the drum, the prism will rotate, and the colors will appear one by one in this small part. So for example, when you will set the color for yellow, say yellow color is here, and you can measure the corresponding wavelength in this scale. Now, to see the other colors, rotate the drum, the prism will rotate, and this spectrum will move, and the colors will appear one by one through this eyepiece of the telescope. Now, this figure is how the object looks under the low pressure sodium vapor lamp. It's pure golden yellow, so all the objects will look like this yellow color. So the error calculation. So we'll start the experiment with low pressure sodium vapor lamp, and to check the error of the instrument, we will measure the yellow wavelength here. If it comes at 589.6 nanometer, then of course there is no error in this instrument. But suppose if our reading is 589 nanometer or 590 nanometer, then there is an error of 0.6 nanometer or 0.4 nanometer. Because we already know that due to the property of the sodium inside the discharge tube, the radiation is at 589.6 nanometer. So you start the experiment and measure the wavelength for yellow and then calculate the error. Now we have to replace this sodium vapor lamp with the other three lamps, that is the tungsten filament and the two CFLs. So instead of this kind of spectrum for LPSP, we will get this continuous spectrum for incandescent lamp. So while measuring the spectrum of the LPSP, you can see there's a line, discrete lines. So we'll get a single wavelength, say 589.6 for yellow, some 600 for this orange, red, etc. So you have to write down that single wavelength value for all the colors that you can see. But for the incandescent lamp, you can see continuous spectrum. All the violet, indigo, blue, all the VGR colors are present in this spectrum. And these are overlapping over each other. It's very difficult to identify them. But you have to observe by your eye estimation, and you have to write the start point and the end point. Means the wavelength range, not the value, a single value. So say for green, you have to write the start point and the end point of green. But in case of the CFL, we will get both line and continuous spectra. This is again a discharge lamp. So you can see that there are few bright lines as well as continuous wavelength in some part. So the top figure is for cool white and the lower figure is for warm white. So if you see these two figures at a time, you see for cool white light, which will emit the bluish light, you can see the maximum radiation is in the bluish greenish region, and it's very minimum in the red yellow orange range. But from the warm white, the maximum radiation is in the yellow reddish region, and it's very less in the lower wavelength region. So from here, from the color appearance of the source, you can have an idea about the spectrum of the source also. And here, during the measurement, we have to write down the value of this discrete lines as well as the range. Means what is the starting point and the end point. Now this is the second part, that is measurement of CCT. It's very easy. You have to place the chromometer under the source, and here we have the sensor of the chromometer. Now there is a basic difference between these two instruments. In constant deviation spectrometer, we are doing the measurement by our eye estimation. We are observing the colors by our bare eye. Whereas in this chromometer, instead of our eye, we have this sensor. So I have already talked about the silicon photocell, right? So this sensor will do the measurement instead of our eye. So we have to place the sensor under the lamp, and we can see the value like this 5155K, which is for cool white CFL, or 2551K, which is for warm white CFL, like this. And we can see this 7393 lux, that is the amount of light falling over the sensor. And the 0.145 or 0.025, these are the other color parameters which are not required here. So we have to write down only the value of the T, the CCT. You have to repeat the process for the other three lamps also. Now this is the table, the four lamps, the colors that you can observe from this spectrum that you will see in this part. You have to write down the colors one by one, and the measured wavelength, it may be a line spectrum or continuous spectrum. So a single value for line and the range for the continuous. Then if there is any error in the instrument, so you have to correct them, whether it's positive error or negative error, and the CCT. So here I have shown only the case for incandescent lamp, because you know that for incandescent lamp, we will get all the colors. So you have to write down the range. Similarly, for the other three lamps, you have to write down the observed colors and the corresponding wavelength. So this is a sample report. You can see the two instruments, constant deviation spectrometer and the chromometer, their range, and the four lamps, their rating in wattage and rated voltage. 60 watt incandescent lamp, 35 watt LPSP lamp, and 9 watt cool white CFL, and 11 watt warm white CFL. This is a sample report for the measurement part. The four lamps. What is the nature of the spectrum? Whether it's line, discrete, continuous, all mixed, and the colors present in the spectrum, and the corresponding wavelength. Say for low pressure sodium vapor lamp, they got this at 589.6 nanometers. So there is no error of the instrument. Zero error is zero. So no need to write the another column or the collected wavelength. So these values are for line spectrum. This is for mixed, the range and the spike or the single value, and the continuous spectrum. This is the measurement of CCT. Now this low pressure sodium vapor lamp, here the CCT is below 2000 Kelvin, which is beyond the range of the chromometer. So we cannot measure this one, but for incandescent and the CFLs, these are the values. So you can see the CCT values of the incandescent lamp and warm white CFL are very close, 2556 and 2798. But instead of that, in spite of that, those two are very close. That means the color appearance of this incandescent lamp and the warm white CFL are very much closer. But in that case also, due to the property of the lamp, due to the light generation phenomena of the lamp, due to the gas discharge phenomena of the CFL, we have the continuous spectra in case of incandescent lamp and the mixed spectra in case of CFL lamp. So although these two values are very close to each other, the spectrum or the wavelength constitute wavelength in case of warm white CFL and the incandescent lamp are very different. So this is all about the experimental part. Now, if you have any question.
Nothing is written in the chat box. There is no question written in the chat box. Nothing is written.
Okay, so you can unmute yourself and ask from any part of the PPT.
Any part of the PPT, yes. This is for final discussion. This is for final discussion. It is very difficult to get into this discussion through this presentation. Really, it is very difficult.
This experiment is very interesting. Like when the students do the experiment, they will very much interested in viewing the colors and measuring. But that's not possible here. But still, if you have any question.
Yes. এটা কি সংগগ কি সংগর্গ কাঞ্জিলাল সংগর কাঞ্জিলাল কে বাবা তুমি কিসব ছবি দিয়েছে দেখো সঙ্গীতা কে কাঞ্জিলাল
Yes, sir.
Yes, any question?
No, sir. I was asking about that CCT and you explained.
Oh, acha. Okay, but from this experimentation portion,
No, sir.
any question how the madam explained regarding how you correlate the measured wavelength values with the CCT? This is very interesting portion. This is very interesting part. How we can correlate these two measured values. One is CCT. On the other hand, the information on the constituent wavelength. Somnath Pal.
Yes, sir.
ঠিক আছে সব?
হ্যাঁ স্যার,
কোনো
আসলে
question নেই তো?
ব্রেক করছিল তাই রিপিট করতে বলেছিলাম একবার।
ও আচ্ছা, না আমার তো এখানে নেটওয়ার্কের একটু প্রবলেম হচ্ছে।
অনেকেই তো আনমিউট আছে এখানে, তোমাদের কোশ্চেন নেই কিছু?
স্যার ম্যাম একটা কোয়েশ্চেন ছিল।
হ্যাঁ হ্যাঁ,
সেটা খুব একটা এটা রিলেটেড না, আমি যেটা বলছি সেটা হচ্ছে যে কোনটা আমাদের ভিশনের পক্ষে খুব ভালো, মানে ব্লু টাইপের লাইট নাকি ইয়েলো টাইপের লাইট?
খুব ভালো মানেটা কি?
খুব
হ্যাঁ,
ভালো
সেটা-
মানে স্যার আমি যতদূর মানে দেখছি, মানে প্র্যাকটিক্যাল এক্সপিরিয়েন্স থেকে দেখছি এলইডি লাইটে খুব তাড়াতাড়ি চোখ কিন্তু খারাপ হয়ে যাচ্ছে স্যার। তাই জন্যই আমি এটা জিজ্ঞেস করছি, মানে কোনটা বেশি ভালো, ইয়েলো টাইপ লাইট ভালো নাকি এই ব্লু টাইপ লাইট এমিশন যেটা হয় সেটা বেশি বেটার?
দেখো ভালোটা তো সাবজেক্টিভ, ওইভাবে তো ঠিক এক্সপ্লেন করা যায় না ভালো খারাপ।
সঞ্চিতা বলবে কিছু?
হ্যাঁ
না,
আপনি
ওরা
বলুন,
অ্যাকচুয়ালি বলতে চাইছে চোখ খারাপ হয়ে যাওয়ার রেসপেক্টে আর কি বলতে চাইছে আর কি।
আপনি বলুন তারপর আমি বলবো।
হ্যাঁ, চোখ খারাপ রেসপেক্টে বলতে চাইছো অ্যাকচুয়ালি কাছ থেকে যে রেডিয়েশন, এই যে ওয়ার্ম হোয়াইট অর কুল হোয়াইট, এই যে ব্লু পোর্শনটা অ্যাকচুয়ালি খুব কাছ থেকে দেখলে পরে, so if the distance between the source and the eye is less, then there is much exposure, impact of exposure is more, so that is not good for our eye. So on the other hand, the warm white, there the blue content is less. So that is more suitable for our vision. So in that sense, in short, we can say that uh, the bluish white, that is cool white LED, is not that much, is more hazardous for our eye when the distance is less. Bhalo noy. Blue white is not good for our health when distance is less. But when distance is more, we should not look directly to the lamp. Suppose you are using a cool white LED lamp in your room, you should not look directly to the lamp from a close distance. But when the distance is more than a few meters, then there is not much significant amount of risk. But warm white is always preferable. অমৃতা বুঝতে পেরেছো?
হ্যাঁ স্যার, থ্যাংক ইউ স্যার।
সঙ্গীতা তুমি কিছু
হ্যাঁ
বলবে?
হ্যাঁ, না ঠিক আছে, ওটাই তো। আর
Sir,
বাকিরা?
but
হ্যাঁ।
in this context, we in generally in electronic device, we always try to hide the blue light emission, like using blue light filter, all these things. Then why we are so much interested in this context? I mean, why we are using such kind of filter to protect our eyes from blue light, where when we are, our eyes get sometimes discomfort.
ওর
Yes,
না আমি
there is,
কেটে গেলাম। হ্যাঁ বলো সঙ্গীতা, আমি বুঝতে পারি।
yes, there is another parameter called circadian system. Okay, like with the natural variation in daylight, if you see the natural variation of daylight, during morning it's more warm kind of sunlight, then during the daytime we get blue light, then again during the sunset we get yellow type light, right? So that is very natural to our body also. Like there is some type of photoreceptor in our brain which can sense the natural variation of daylight, which is completely different from our eye, right? So that receptor, uh, uh, it controls our sleep time, it controls our other health phenomenon also. So during night time, if you are under blue daylight, so our body will be stimulated, like we will stay very much awake. Instead of falling asleep, you will be very much awake. So if you see your smartphone, there are also that blue light filter, or there is a option for changing the colors also. Like you can change the color of your screen. It may be cool, it may be warm. So it's advisable that during the daytime you can be under cool daylight, but after sunset, if you are under warm daylight, that is more helpful for our health. Like after some time we should fall asleep. So if you are under, yes, during night time. So if you are under blue light for a long time during the night time, so that affects your sleep cycle, that affects your mental issue, etc., etc. So that's why there are this word blue light hazard, blue light filter, like this. Okay, so during night time you should not be under very cool light for a long time. So that for that reason you can see that there's an option for cool screen or warm screen in your smartphone.
Blue light filter is there. There is
Yes,
option
yes.
blue light filter, yes.
Yes, ma'am, got it.
Okay.
Actually, basically for the blues in our neurons, which is affected by
Yes,
the.
yes. Yes.
But time is important. At what time it is required? That is the issue. Time is important actually, Somnath.
স্যার আমার একটা কোয়েশ্চেন ছিল,
হুম।
বলছি যে আমরা যখন দেখবো টেলিস্কোপ দিয়ে, তখন আমরা কি লাইন স্পেক্টর দেখতে পাবো না কন্টিনিউয়াস? আর কন্টিনিউয়াসটা তাহলে কখন দেখতে পাবো?
সঙ্গীতা
হ্যাঁ, আমি করছি।
বলো।
হ্যাঁ, বলছিলাম যে যখন টেলিস্কোপ দিয়ে দেখবো তখন লাইন স্পেক্টর দেখতে পাবো নাকি কন্টিনিউয়াস?
হ্যাঁ, ধরো তুমি এখানে থাকবে, তো আমি এখানে চোখ রেখে এই টেলিস্কোপ দিয়ে দেখবো, তো এই স্পেকট্রামটার যে কোনো পার্ট মে অ্যাপিয়ার থ্রু দিস টেলিস্কোপ, এনি পার্ট অফ দ্য স্পেকট্রাম মে অ্যাপিয়ার থ্রু দিস টেলিস্কোপ, whether it's line or continuous, any part of this spectrum will be visible in this part. But for the measurement, we have to set the colors one by one. So it doesn't matter whether it is line or whether it is continuous. You can see yellow, you can see red, or you can see black over this telescope. Okay, so for the measurement purpose, we have to rotate the drum, we have to rotate the prism, the colors will appear one by one. Because from this small, narrow opening, it's not possible to view the entire spectrum at a time. So if the lamp is LPSB, before the collimator, you will see either some line or black part, or if the lamp is incandescent lamp, you can see any color because it's continuous spectrum.
তাহলে ওই ইনক্যান্ডেসেন্টেই কন্টিনিউয়াসে থাকবে।
হ্যাঁ, incandescent হলে যে কোনো একটা পার্ট ওখানে পড়বে, so you can see continuous part.
ওকে
But in this
কন্টিনিউয়াসে পিকটা কি করে বুঝবো আমরা? ইন্টেন্সিটি দেখে?
ইন্টেন্সিটি আমরা বুঝতে পারি না, মানে এখানে চোখে দেখে যেটা আমরা বুঝি সেটা অলওয়েজ দ্যাট কোরিলেটস দি অ্যামাউন্ট অফ রেডিয়েটেড পাওয়ার, ইট ইজ নট দ্যাট। That instrumentation is something different. From this instrumentation, it is not possible to get the value of the associated power. Only thing we can have what are the color, what is the nature of the spectrum, what are the color, this much of, and we can get the data regarding for the wavelength. That much we can have with the help of this constant deviation spectrometer.
ওকে স্যার।
Because it's sir has already explained that it's one-dimensional plot, so you can see only this x-axis here, not the amount of power.
That instrument name is the spectroradiometer. Spectroradiometer. You know the radiometer, actually the instrument which can measure the radiation power. So that is spectroradiometer. Here it is name is spectrometer. So from the name, you can understand with the help of spectrometer, we can have the information related to wavelength also. And with spectroradiometer, this kind of two-dimensional plot we can get. The instrumentation is totally different. Instrument is totally different. Spectroradiometer.
Sir, so in this context, as in case of incandescent lamp, all the colors are diluted with each other. So
all the colors are
they are diluted. In only yellow or red colors are more prominent. So only we can see the only that color, yellow or green, because we have informed us that only we can see one color at a time through telescope. So in case of
no, one color at a time through telescope, but without when you just with your eye, when you look at to the lamp, without any instrument, you can just with your bare eye, when you look at to any the burning incandescent lamp, what is the color? Color is yellow.
Yes, yellow.
What actually this experimental result helps us to understand why it is yellow and what is the nature of the spectrum.
Okay.
Why yellow? Because the power content, it is actually the power content. We are not able to right now with the constant deviation spectrometer, it is not possible for us to get the associated, get the value of the associated power, but we can see what is the presence of wavelength, which portion is bright. Say for example, this low pressure sodium vapor lamp, the brightest line is yellow. That's why the appearance is bright. But we are not able to measure the power. Okay.
Yes, sir.
তোমরা এর পরেও মানে it is not that we have finished here. So after that you have the email ID of Sangita madam. You can put your question on email. 1 minute.
Yes, if you have any query, you can send it to me. Anything else? আর কিছু
No.
কোয়েশ্চেন বাকিদের?
Ma'am, do you have to submit any kind of report on this experiment?
No, not yet. If anything is required, I will inform you.
Okay, ma'am.
হ্যালো সঙ্গীতা,
হ্যাঁ,
ওরা কিছু জিজ্ঞাসা করছে?
না আর তো কিছু কোয়েশ্চেন। ওর বলছে রিপোর্ট লাগবে কিনা, রিপোর্ট তো এখনই কিছু তো লাগবে না।
এখনই কিছু লাগবে না, কিন্তু তোমাদের তোমরা কি বুঝলে সেটা একটু লিখে ফেলো তো, জাস্ট ইউ রাইট ডাউন একটা করুক না।
আচ্ছা ঠিক আছে।
With the help, you have the laboratory instruction sheet. You have the laboratory instruction sheet. Have you got it?
Yes, sir.
Yes, sir.
Laboratory, so laboratory instruction sheet is available to you. So what we have discussed, madam will send this PPT.
Yes.
So you just write down about your understanding of the procedure, the instrument, and the background theory. Write a report, no issue. And as I said, you can put your question over email. We will answer back. Okay.
Okay, sir.
সঙ্গীতা, তাহলে তুমি কনক্লুড করো।
হ্যাঁ, ওদের অ্যাটেন্ডেন্সটা কি আমি স্ক্রিনশট নিয়েছি, বাট কল করবেন কি না?
ও আচ্ছা, একটু দেখে নি তাহলে, পরপর আমি একটু নামগুলো ডাকি, ওরা একটু রেসপন্স করুক। হ্যাঁ, আচ্ছা, অভিষেক মজুমদার,
প্রেজেন্ট স্যার।
রোল নাম্বার কত?
59।
আচ্ছা, আবির চ্যাটার্জি।
আমার কাছে রোল শিট আছে, আমি কি শেয়ার করব? সুবিধা হবে তাতে নাকি কল?
প্রেজেন্ট স্যার। আবির চ্যাটার্জি প্রেজেন্ট স্যার, রোল 52।
আবির
প্রেজেন্ট স্যার।
আদিত্য রায়
Present, sir. Present, sir. 54.
আচ্ছা, তারপরে কি? ঐশানী
Present, sir. Oishani. Roll number 63.
আচ্ছা, তারপরে কি? অলোক কি?
আমি কি রোল শিট শেয়ার করব?
আচ্ছা, করো।
হ্যাঁ, সেটা বোধহয় সুবিধা হবে।
তোমার নামটা কি? অলোক
Sir, Alak Jari Murmu.
অলোক
Jari Murmu.
অলোক জারি মুর্মু। আচ্ছা,
17 roll number.
ওকে, আমি ম্যাডাম রিপিট করেছি, একটু বলছি। সঙ্গীতা, তুমি বলবে?
হ্যাঁ, রোল নাম্বার 2।
Yes, ma'am. Ankit, yes, ma'am.
6,
Yes, ma'am. Kaushik Magic.
9, Swapnil,
Yes, ma'am. Swapnil Kisco. Yes, sir.
10, Deepten,
Yes, ma'am. Present.
হ্যাঁ,
Deepten
30,
Mardi.
okay,
Yes, ma'am.
okay, 15,
Yes, ma'am. Mohammad Ali Amjan.
17,
Yes, ma'am.
18, Rajkumar,
Yes, ma'am. Raj.
19, Iqbal,
Yes, ma'am. Iqbal.
20,
Yes, ma'am. Unkush. Yes, ma'am. Present.
21, Yusuf, 21, Yusuf Ali, 22, Arman, 22, Arman, 23, Shaheen Akhtar,
Yes, ma'am.
24, Parvez,
Yes, ma'am.
26, Ritam,
Yes, ma'am.
27, Dipankar,
Yes, ma'am.
29, Golam,
Yes, ma'am.
1003, Saurabh, 1003, Saurabh, 13, Sobuj, 1002, Vikas,
Yes, ma'am.
1003 Somnath.
Yes, ma'am.
4 Arijit.
Yes, ma'am. 104 Arjit.
5 Rajit.
Present, ma'am.
8 Shubham. 8 Shubham. 10 Shubhadeep.
Yes, ma'am.
15 Ujjwal.
Yes, ma'am.
30 Debargho.
Present, ma'am.
31 Subroto.
Present, ma'am. Subroto Mahato.
32 Arnav.
Yes, ma'am.
34.
Present, ma'am.
35 Saurabh. Saurabh Orao 35. 36 Shaikh Rahman. 36. 37 Sohel.
Yes, ma'am.
38 Sodeep.
Yes, ma'am. Showdeep.
40 Shalik.
Present, ma'am.
41 Jion Sheikh. 41
41.
44
Present, ma'am.
41
Shubhoshri.
47
Present, ma'am.
তো আছে, 49 সুপ্রতীক।
তো সঙ্গীতা 44 47 আছে তো?
হ্যাঁ 47 তো আছে।
Present, sir.
44 ও আছে।
হ্যাঁ 44 আছে। 49 সুপ্রতীক। নেই। 52 আবির চ্যাটার্জি।
Present, ma'am.
53 কনিষ্ক বসাক।
Present, ma'am.
54 আদিত্য।
Yes, ma'am.
58 প্রতীক।
Yes, ma'am. Yes, ma'am.
59 অভিষেক।
Present, ma'am.
60 সোহম।
Present, ma'am.
হ্যাঁ
60
কে বল-
present.
কে বলছো? হ্যাঁ হ্যাঁ বলো। 1007 বাপি। 9 অমৃতা।
Yes, ma'am. Present.
Ma'am, Hasibur Rahman, 1006.
আচ্ছা 11 সৌরভ।
Yes, ma'am.
12 সন্দীপ।
Yes, ma'am.
13 শঙ্খ।
Yes, ma'am.
14 সৌগত।
Yes, ma'am.
Hello, ma'am.
হ্যাঁ হ্যাঁ কে
Ma'am,
বলছো?
আমি 41. I'm 41. Ijwan Sheikh.
41
ও হ্যাঁ 41 অ্যাবসেন্ট
Yes,
হয়ে
ma'am.
গিয়েছে রাইট।
হ্যাঁ, ma'am.
ঠিক আছে।
I'm 36.
36 হ্যাঁ
36
36 তো অ্যাবসেন্ট ছিল।
শায়েক রহমান।
তোমরা কোথায় ছিলে?
Ma'am, ছিলাম আমার কানেকশন একটু ইয়ে হয়ে গেছিল। নেট কানেকশন।
ঐশানী
Present, ma'am.
তোমরা একটু আনমিউট করে নাও যাদের হয়ে গেছে।
রিজিয়ন একটু
Unmute
আনমিউট
করে
করো।
নাও। 64 দিয়া।
Present, ma'am.
65 পাঞ্চালি।
Present, ma'am.
66 অনিরুদ্ধ।
Yes, ma'am.
67 মানস। 67 মানস পাত্র। 69 শুভঙ্কর। 70 সমীরণ।
Present, ma'am.
71 রাহুল। রাহুল দাস 71। 73 নিলয়।
Present, ma'am.
রাহুল আছো?
No, Nilay.
হ্যাঁ নিলয়। 74 শ্রেয়স।
Ma'am, ও গ্রুপে
ওর নেটওয়ার্কটা একটু খারাপ আছে আর কি।
গ্রুপে
তাই ম্যাম ও মানে ও মাল্টিপল টাইমস এন্টার করেছে যেহেতু এই জন্য ম্যাম ও মানে এখন রেসপন্ড করতে পারছে না।
নেটটা একটু খারাপ আছে।
ও নেটের প্রবলেম আর কি।
হ্যাঁ। 77 ব্রজেশ্বর, 77 ব্রজেশ্বর সর্দার, 78 সুকেশ মুর্মু,
Yes, ma'am.
82 সাথী,
Yes, ma'am.
85 জিশান রহমান,
Yes, ma'am.
88 সম্পদ বড়ুয়া, 88, 89 মোহাম্মদ কাইফ,
Yes, ma'am.
91 সুপ্রতিম,
Yes, ma'am.
92 সায়ন।
Present, ma'am. Present.
ম্যাম 1009 অমৃতা,
অমৃতা কত?
1009 ল্যাটারাল।
1009, ওকে ঠিক আছে।